In the given scenario, a wave is generated with 5 pulses per second with a wavelength of 3 meters. The first crest travels 45 meters in 9 seconds. How fast is the wave moving? Choose one of the methods below to solve for the speed. In this scenario, all of the variables are accounted for, which means you could solve using method 1, method 2, or method 3 based on the information that you focused on. Be careful though. That means that if you're focusing on 2 of the variables, that means there's at least 1 or 2 more that may be considered distractors. Make sure that if you choose a method, you use the right values to substitute in. Take a moment, couple minutes, try one of the methods, and then we'll compare all 3 methods. Pause the video and start it up when we're ready to discuss the final answers. Method 1 is similar to how we calculated velocity at the very beginning of the year. We took a known distance and a known time. In this case, we know that the first crest travels 45 meters in 9 seconds. This is similar to how we recorded data in our labs. So I would set up my formula with my given variables. 45 is my distance, 45 meters, and 9 is the amount of time that it traveled 45 meters. 45 divided by 9 gives me 5 meters per second. You would use this method if you know the amount of time it took a wave to travel a known distance. With the next method, we have velocity equals frequency times wavelength. We need to know the frequency and we need to know the wavelength in this case. What's confusing about this problem is it doesn't flat out say, here is the frequency. It tells us our wavelength is 3 meters, which is good because it could be confusing. The wavelength is 3 meters, but the crest traveled 45 meters. There may be the same unit in a problem like this. My frequency represents the number of waves or pulses over time. In this case, the wave is generated with 5 pulses for every 3 seconds. Wavelength is 3 meters, so velocity equals 5 divided by 3 pulses per second. 3 meters is my wavelength. So I could either turn 5/3 into a decimal or 5 times 3 divided by 3. Regardless of how I calculate that answer, I end up with a velocity of 5 meters per second. Now this is for scenarios where you're not told this is a frequency, not told this is the period. Well, you need to know that it's a ratio of pulses per second for frequency. The period's the exact opposite. It's seconds per pulse or wave. So if we had 5/3 for our frequency, our period is 3/5 or 3 divided by 5. So velocity equals 3 divided by 5 over 3. The wavelength's the same. 3 divided by 5 divided by 3 is going to give me 5 meters per second again. Either method, as long as we're dealing with the same exact wave, is going to give us the same exact velocity. Next, let's talk about some of the labs that we've done in the last couple of days. In our first lab, we looked at the speed of a wave using method 1 to calculate the speed. We noticed that the amplitude did not change the wave. The amplitude represents how much energy is in the wave, which does not represent the speed of the wave. The pulse width in this case did not change the wave at all. It didn't speed it up, it didn't slow it down. The only variable that altered the speed of the wave was the tension in the string. We noticed this as we calculated the velocities. It increased as we went from low, medium to high tension. And also we visibly saw it move a lot faster when it went through that medium, the string. If we think of different tensions in the way that different materials might create different tensions, a tightly wound spring is going to be more tense or have more tension than a loose slinky. Since the only thing that affects the speed of a wave is the tension, when the medium changes, the velocity changes. This is an observation that becomes very important when we get into sound and when we get into water waves a little more deeply. Water, deeply. McNear's laughing at least, right? We've started to observe how waves act as they pass through a medium, but what happens when they bounce off a barrier or reflect off of a barrier? We looked at two types of reflections, fixed end and loose end, or open end, it's sometimes called. Waves move the same speed after they reflect. In all cases, we recorded that the velocity of the wave before was similar or close enough to be the same as the velocity after. Any variation in that would have to do more with human error than anything. The only thing that could slow down that wave would be if there was damping, or consider it friction within the wave, or as it rubbed against the pole, because there was that loose end with the ring around the pole. We could have created friction there. Since we turned off damping, we assumed that all energy that went in is equal to all of the energy that came out. We've seen this before. We've observed energy transfer and energy being conserved. Beyond the speed of the wave after it reflects, we notice that different barriers create different shapes or treat the wave a little bit differently as it reflects out. A fixed end reflection inverts the wave. If the pulse came in upward, it came out downward. It inverted it. It flipped it over. Whereas a free end reflection keeps the wave moving the same direction. If it comes out on top, the pulse goes back out on top. If it comes in on the bottom, it goes out on the bottom. Light waves act like this. When you look at a mirror, it is a free end reflection. When I look at my head in the mirror, I see my head. I don't have to look at my inverted image. I don't have to look at my feet to see where my head is in the mirror. It doesn't invert or flip my image, doesn't flip those light waves.